we only actually have to measure 2 of these because 100% of the mineral soil is going to be made up of these 3 size fractions. So if you measure 2, you just add those together, subtract them from 100, and you get the third. And sometimes that's a good check when you plot something, because you have, if you have 50% clay, for example, you must be on this line somewhere at 50% clay. And so then if you know that you have 40% sand, 40% sand has to lie along this line. And so where those 2 lines cross must be where you are. And so from that, you could read off what your percent silt is, which is 10%. Okay. Sort of just a quick reminder that we do have to think a little bit about this word clay is always something we have to keep in mind, because we talk about it in 2 different contexts, right? We can talk about clay as a size, right? So clay is less than 0.002 millimeters. But there also are clay minerals, which are sheet silicates. So clay minerals have a specific crystal structure. The clay size fraction is just anything that's below 0.002 millimeters. And for the most part, a lot of clay minerals end up falling in that clay size category. So you have a clay sized clay. But your clay size fraction can also have other minerals. So that's important to keep in mind. It's unfortunate, but that's a little bit confusing. Okay. But we've talked a fair bit about that. The other thing we've mentioned before, this is important, and this is actually in your field book. So you certainly don't have to memorize this, but it is important to just keep in mind there are a few discrepancies for different textural classifications. And there are a few discrepancies. We'll always use the USDA classification unless we're, we explicitly say we're using something different. But for example, there's some international classifications where they define silt at a smaller size fraction than sand. The same with this AASHTO classification. This is something that's used basically in engineering. And so they also have slightly different subdivisions for clay and silt. But the other thing that's important on here with texture, even though generally like the tests we'll do in the field are really aimed at determining the relative percentages of clay, silt, and sand, there can be larger things in the soil as well, especially when you get into the sea horizon, right? Because the sea horizon is transitional into the regolith or the bedrock. And so as you get closer to the bedrock, we might expect you actually might start to find fragments of the bedrock that have not broken down yet. And so if you see them, there is another set of measurements and terms that we use to talk about those larger fragments. And the words are relatively familiar. You've probably all heard the word gravel and stone and boulder. But as in a lot of discussions, what's important if we're in the field and we're doing kind of a scientific evaluation of an area, gravel means something specific. So you really, if you're going to call something gravel in your field notebook, when you're out looking at a soil, that means it's got a certain range of size particles, and you can't just call anything coarser than a sand gravel. But this has got the, so gravel is between 2 millimeters and 76 millimeters. Cobble is 76 to 250. Boulders are greater than 60 centimeters. So they're not quite a meter. So those are pretty big, right? A meter is just over 3 feet. So that's, those are pretty big things. And then we actually, the first thing you do is a textural modifier. And again, this is from the handbooks. You don't have to memorize this, but if you've got less than 15% by volume fragments that are larger than sand, you just would go with the typical soil textural name. And then as you start to get higher percentages of fragments, then you modify your textural name by adding, gravelly loam, or very gravelly loam, or extremely gravelly loam if you've got more than 60%. of gravel fragments in it. Okay, does that make sense? Okay, so let's dodge out of here for a second, Ben, and go ahead and watch a video. So these, like I said, these videos are from University of Saskatchewan. We don't talk a ton about Canada directly, but of course, agriculture is hugely important in Canada. They have a lot of, especially our northern prairies are very similar to the prairie provinces of Canada, and they produce a large percentage of the world's grains and corns and wheat. So agriculture in the eastern part of Alberta, in Saskatchewan, in Manitoba, agriculture is huge there. So soils are also really important, and there's lots of work that goes into teaching people how to, do the same thing that you guys are learning how to do too. Anyways, so let's start with these. These are all by a guy named Professor Dan, and I think he does a good job. So hopefully you guys will enjoy this. I'm going and this first one, don't worry about taking notes. We'll just watch it and discuss it very briefly. The second two, I might get you to take some notes because they're it's a little bit more structured and things that we haven't talked as much about yet. Okay, so the first one we'll do here is soil texture. Can everyone hear that? Okay, let me see if I can. I'm not quite sure what I have to do here. We'll try this now and see.
Important physical property of the
Is that
soil.
better?
Soil texture is the relative proportion of sand, silt, and clay in the soil sample, and it controls many of the physical properties such as drainage or erosion resistant that are essential for proper soil management. The three soil separates, sand, silt, and clay, have very different feels when we use our hands. So a sand, for example, is obviously gritty, a grittiness. Silt is very smooth or silky, whereas clay has electrically charged surfaces and is very sticky when moist. So the three materials feel very differently in their pure form, but in soils, what we get are combinations of sand, silt, and clay. So a combination of 33% of each, we would call a loam. When we're in the field, we use what's called a textural triangle, which has 13 different particle size classes in it, or textural classes. And in the field, we use our hands to place the soil sample into one of those 13 classes. We do this using three different tests: the ball test, the ribbon test, and the field test. Some people as well, instead of a ribbon test, use a wire test, but we're going to use the ribbon test today. And basically, the way to think about all of these is that clay gives stickiness to a sample. So the higher the sample is in clay, the stickier it is and the more cohesive it is. So a sample which is 100% sand will have no cohesion and will fall apart very easily. So that's really what underlies a lot of the tests we're going to be looking at today. Now, the first test is the ball test. And what I've done is taken a sample from each of our three horizons, the A, B, and C, and put them up here, and I'll be accessing them for the test. So I'll begin with the C horizon. Again, remember, lots of calcium carbon in it, that lighter color. I break the sample up into smaller parts, and then I add moisture to it. I don't want to saturate it, but I want to make it to see if I can form a ball. So I manipulate it, I add sufficient water. If I've added too much water, I can add some dry soil to it. Okay, and I'm trying to see if it forms a ball. And indeed, it forms a very cohesive ball in my hand. If it didn't form a ball, it would tell me that it's very high in sand, a loamy sand or a pure sand. So our first test eliminates the very high sand soils from the other soils. The next test I do is the ribbon test. And in the ribbon test, what I do is I use that ball and I try to extrude it between my thumb and my forefinger. And what I'm doing is squeezing it out or extruding it until the point that it breaks. And when it breaks, I take it and I measure it against a ruler. So that ribbon was about 4 centimeters long. And I'll do it again just to see if I get a similar result. I need to make sure it stays at the right moisture. So I extrude it once more between my thumb and my forefinger. And again, I'll compare that to my ruler. And that one was about 3 centimeters. So when I look at my ribbon test, there are 3 categories of length: less than 2.5 centimeters, 2.5 to 5, or greater than 5 centimeters. So this falls into the 2.5 to 5 centimeter length. And I've narrowed it down then to sandy clay loam, silty clay loam, or clay loam. And now I need to determine which of those 3 final classes it is. And I do that using what's called the field test. So I place a small amount in the middle of my hand and I saturate it. I rub my finger on it, and I'm trying to determine the dominant feel to this. So the questions are, is it very gritty? Is it very smooth? Or is it neither smooth or gritty? And when I feel this, it has a considerable amount of grit or sand in it. So I'm going to say that it's a very gritty material. So when I go to the section of the handbook for the field test, this soil feels very gritty and it classifies out as a sandy clay loam. So I'm going to repeat that now for my other samples. You don't want to wear your good clothing out in the field when you're doing soils research. So now I'm taking a sample of that B horizon. I break it up. Again, I want to remove any stones from it. So I break up that horizon, removing any stones. I add my moisture to do the ball test again. And again, the soil's forming a very nice ball, so it's not a loamy sand or a sand. I'm going to take it and try to extrude out my sample. So it's a longer ribbon this time. It's breaking about now. When I measure the length, it's about 6 centimeters long. So I'll do that again just to confirm that measurement. And it's very important we have the right amount of soil so we don't run out of soil when we're extruding it. So I'm extruding it again. Nice long ribbon. Okay, just broke off, measuring it again about 6 centimeters. So I'm now in a category of 5 centimeters or above, and that takes me to the column that includes sandy clay, silty clay, and clay. So I want to clean off the middle of my hand, put a small amount in there for the field test, saturate it, and feel. Remember, I'm feeling for, is it gritty, is it smooth, or is it neither gritty or smooth? And once again, I'm feeling lots of grit in here. So I'm going to say it's very gritty, and that would be a sandy clay. So We'll turn then to our final horizon, the A horizon. The A horizon has lots of roots in it, and we need to make sure we pull those roots out before we start.
We're going to just jump ahead because we don't need to watch this again. We'll go to this is talking more
clay
about
loam, silty clay loam, or clay loam.
larger fragments.
I take it for the final field test. I clean the legacy of the last test out of my palm, put it in the middle. Is what we call glacial till. And it's directly deposited by the ice sheets. The ice sheet's effectively a large bulldozer, mixes together gravel, sand, silt, and clay, and gives us this characteristic glacial till parent material. The last thing we'll look at is the percentage of coarse fragments. So anything larger than 2 millimeters in diameter, we consider to be a coarse fragment, or gravel, more simply. And what we want to do is try to get a sense of what is the percentage of coarse fragments in this profile. And what we use for that is a chart called the area covered chart. They are charts that simply give us a white space with different black objects in it, which occupy in this 2% of the white space of that chart. This chart is 20% coverage by the black spaces. And we use this to try to calibrate our estimation of coarse fragments or of other features in the soil. So by coarse fragments, you can see the larger gravel pieces associated with this. And for where I'm sitting, there are small gravel entities as well. But the percentage of them is relatively low. So if I compare it to my area covered chart, it would almost certainly fall into this 2% or slightly more chart. So I would say that for the C horizon, there's 2 to 5% coarse fragments. The B horizon, 2 to 5% coarse fragments, but I can't actually see any coarse fragments in the upper A horizon. Those two big stones over there I took from the bottom and took up there. So our A horizon seems to be relatively stone-free, so I would say it has 0% coarse fragments. Between our coarse fragments and our soil texture, we have then described the key physical properties of the soil for many management processes.
Okay. So did that make sense to you guys? Pretty straightforward. We have a slightly different flow chart for determining soil texture that you guys, I think, have already looked at, but it basically does the same thing. But that's sort of a good visual to show you how much to wet the soil, how to extrude the worms, and how to get a sense of the feel. You do have in the back, so the back of your soil manual, there's a miscellaneous section, and you've actually got a bunch of these charts like the ones he was showing, but they go into even finer divisions for estimating the percentage of things in soils. So when you're estimating your soil percentages, you literally just, like he said, you hold this book up to the outcrop and you just try to match. In this case, the coarse fragments are the black things, and you just try to figure out, between the dark and the light, what comes close to the percentages that you're seeing, and then it's got the area percent calculated there. Okay. So that's a relatively easy field estimate to do. All right. Okay, so let's go on. So the next thing is soil structure. And I think we've already done this, so I'm going to go through this pretty quickly and get to consistence, because I want to watch this last video, and it'll take about 8 minutes. So, but for soil structure, we've talked about these things before, right? These are, we talked about the platy versus the columnar versus granular versus blocky. And we talked about this a week or two ago. So this is just another review of that. And if you watch, I do have a video uploaded with the same guy, Professor Dan, where he goes through at that same outcrop and talks about how to determine soil structure. Okay, but since we've talked about this before and we've looked at some pictures, you guys, I don't think we need to watch that video right now. And again, this is your field manual, right? These are actually the pages from your NRCS field book. So when you're in the field, if you do this a lot, eventually you would need the field book. You just would recognize these things. But almost all the things that we describe in the field, you can find pictures of in your field manual, right? So that's why this is an incredibly useful thing. So then the next thing is consistence. And this is basically how well the individual PEDs or little clods hold together. There's 4 things we talk about. We can talk about rupture resistance. When you have a little dirt clod, how much pressure do you have to apply to break it? And that's a rupture resistance. We can talk about stickiness. So you take a little bit of soil between your 2 fingers and pinch them together. And when you pull your fingers apart, that upper example is non-sticky. So that would be what size particle do you think is going to dominate a non-sticky? Sand, silt, or clay?
Sand.
Sand, yeah. And you can actually see the sand fragments. On the other hand, the other extreme is this picture below. We have got lots of clay. When you try to pull your fingers apart, like it sticks together. It's very cohesive or sticky. We can also look at plasticity, and basically that's another little field test you can do where you try to make little rods or little worms to see how plastic the soil is, and you can measure the diameter and you can measure the length to classify into non-plastic versus very plastic. And the last thing is penetration resistance, and this is a bit trickier to do. You can see the picture on the right. That's a soil penetrometer, and it actually measures how much force you have to apply to get a certain surface area to go into the soil. And that's something it's a little bit harder to do without a specific tool, although you can certainly do some relative things. You're taking something like a pencil and trying to push it in the soil, and just to get a sense of what the relative penetration resistance is. If you were doing this, like I said, for a company, for example, if you're doing some kind of site assessment and you were going out to do soil descriptions, they would give you a penetrometer. You can get the penetrometers you can get for 40 or 50 bucks, and they actually have a little spring that's calibrated to the amount of force it takes to push something down to the soil. But those are the 4 typical measurements we talk about when you are determining the consistence of the soil. Like I said, the first 3 are relatively easy to do in the field. So you can do those things relatively easily on your own without needing any kind of special equipment. Okay. So any questions about that? Okay, so let's see how you do this. Let's jump back with Professor Dan here and check out this last video that we'll watch today, which is the consistence one. I'm gonna put it there. Is that right? Yeah. And this is.
Our final video will be looking at soil consistence, which is very closely related to soil structure, which we looked at in our last video. Basically, we want to know how will those PEDs behave when they're subject to a disruption, or how will they behave when they're very wet? And that's what the consistence test tells us. There's 2 types of consistence. They're depending on the moisture level. So the one category would be moist or dry consistence, and the other one is wet consistence or stickiness. Now this profile is quite dry, so we'll be doing the dry consistence test, and then follow that with the wet consistent or stickiness test. So for consistence, what we're going to do is subject the PED to a force. And the force for dry consistence, the least force will be squeezing it between my thumb and forefinger, or I can try to squeeze it in my hand, which has higher pressure, or with my foot, which would be the highest pressure of all. So an escalating scale of force to see how the PED will withstand that. And it's one of the things we look at consistence for example, is compaction. So if a vehicle moves over the soil or a hoofed animal does, that's putting a stress on those structural units, and how resistant will they be to that stress when it's imposed on it. So consistency is very useful for looking at issues like soil compaction. So we'll begin with the A horizon. So we're doing a dry consistence tests. We put it between the thumb and the forefinger and we squeeze it. And in fact, that granular unit fell apart very easily. So I'll get another one. Small granular units, and they fall apart with very little force being exerted. So in terms of the structure then, they offered a little bit of resistance, and we would say they're slightly hard as our dry consistence class. The B horizon, what we want to do is get a piece that's not quite this large, so we can trim it down a bit until it's more about 1 inch by 1 inch or so. And that way we get a sort of a standard comparison for much larger units. So I'll just trim that down, and we're going to use this for our consistence test. That's about the optimum size. So I begin with subjecting it to pressure with my thumb and forefinger, and I can't break that apart with the maximum force I can exert. I'll use my other forefinger for this one too, and I can't break that apart. If I put it between my hands and add pressure that way, again, even at maximum, almost superhuman strength, I can't break that apart. So finally, I add my maximum pressure to it by putting it on a hard surface and stepping on it, and then it breaks apart. Okay, so having added that final amount of pressure, I was able to break it apart. But obviously very resistant to disturbance, and equally very resistant to penetration by a plant root, for example. So that B horizon, a very dense material. And in my dry consistence classes, that's extremely hard. If I couldn't break it apart with my foot, it would be rigid as a consistence class. The C horizon, here's a good size to try with that. So I apply my thumb and my forefinger. I'm unable to break that apart. I put it between my hands, and it crushes. Okay, so it's crushed at that point. And as a consistence class, that's a hard consistence class. So the A horizon then had relatively low consistence, broke apart quite easily penetrated by roots or by burrowing animals. The B horizon, much more resistant, extremely hard. And the C horizon, somewhere intermediate, a hard dry consistence class. Now, the wet consistence then, what I want to do is add sufficient moisture. So I break it up just like we did for the texture test. I moisten it, and in fact, I saturate it this time, wetter than I did for the texture test. So making sure it's saturated. And what I'm going to do is put a little bit of it between my thumb and forefinger. I'm going to put some pressure on it, and I'm going to release the pressure. And what I'm looking for is, does the material adhere to my fingers? And when I release it, will it actually stretch and maintain its contact between the two fingers. And basically, the higher the clay content, the greater the stickiness, and the more it will stretch between my two fingers. So it's very closely related to the clay content. And this test tells us, for example, how well will the soil bear a strength when it's wet? I mean, are you likely to get stuck or not in a soil? And basically, the higher the stickiness, the easier it is to get stuck in a soil like that. Okay, so I've just put a small amount between my thumb and my forefinger. I press on it and I release. Okay, and what you can see is it's maintained on my forefinger, but there's nothing left on my thumb. And there was no stretching whatsoever. So it released very quickly from one finger and remained on the other finger. The lowest consistence class, it wouldn't retain either. It would just fall away. This is the second consistence class, and we would say that this is slightly sticky, okay? Because it's maintaining its contact with one of the digits, but there's no stretching. For a truly sticky one, it would actually stretch between the two fingers for quite a distance before it broke. So this would be slightly sticky, and in fact, the other two horizons are slightly sticky as well. They're quite similar in terms of texture, and hence we would expect, and they do behave the same way for our wet consistence class.
Okay. Yeah. So, does anyone have any questions about that? Do you think you could reproduce all those things?
Today we're assessing a really important soil characteristic,
Hold
and
on.
that's called soil texture.
I've got
Before we go on to our test, it's worth appreciating.
my YouTube started up again here. Okay, there we go. Yeah. So anyway, so those are the some of the ways that you test for consistency, and at least to me, when I saw those videos, as I watched them, they seem like they're relatively clear and descriptive as far as what you would need to do for determining these things. Okay. So in the field, did anyone get out and dig any holes over the weekend to look at soils? Yeah. So anyone mind sharing with us what you saw? Jackie, what did you see when you dug? How deep could you go? Did you see any difference in colors or anything like that?
Yeah, I did. I saw a pretty diverse color range. Most of my soils were really sandy, but then kind of in the middle of the barrier island is really dark, and then the edges were like light and sandy.
Oh wow. Okay. So you already have some idea, when you think of soil textures, at least for the upper horizons, you already have an idea where you're going to sit on soil texture charts probably when you actually do some of the tests. So that's great. Odin, what did you see when you went out digging?
Well, I dug in my garden, and that was kind of interesting, just kind of seeing how the organic material has built up over the few years. And then yeah, kind of down below, it's pretty sandy, pretty kind of just brown, not super different horizons or anything. Pretty uniform. And then I was going to dig out in the field behind my house, but I didn't want to disturb it too much, so just kind of dug a little hole.
Okay. Yeah. I mean, it is, places where sometimes you can see like where a road's gone through some fields, at the edge of the road, sometimes that's kind of a natural place you can see a little bit deeper. Although obviously if you're by a road, you have to be very careful pulling off the side of the road to make sure you're totally off. But otherwise, you can get down a foot or 2 feet in a hole. Most places that will put you through the A horizon in a lot of cases anyway, so you can see some, hopefully see some variation. Isabel, how about your hole? What'd you find?
So I generally stayed in the A horizon and just kind of sampled a bunch of different places around my yard. And it was pretty clayey and loamy.
Yeah. So did you go through and do the soil texture test with that flow sheet?
Yeah.
Oh, very cool. So if you did anyone else go and dig and try anything yet? Okay, Toby, you were moving. You're in a new environment, so you definitely should find a place to go and dig. Although,
I was able to get. I didn't have a shovel at the place that we're staying, so I had a spoon. So I couldn't get super far. So stayed pretty much in the A horizon and moved around throughout our yard.
okay. Well, so the other thing is when you're in kind of steep environments, which a number of you may have this, but especially when I think of the mountains, a lot of times if you can find a stream, and again, not a stream that's really big, you don't want to get too wet or fall in. But a lot of times stream banks are really great exposures as well to see soils, because the stream a lot of times will cut down through. And because the stream is a place where there's lots of sediment transported and deposited, especially in mountainous areas, we have a lot of topography. A lot of times you don't get really thick soils, on the sides of hills and things like that, because things are being transported because you've got steep gradients. But where you have streams, usually in the stream valley, you'll also have things deposited periodically. And so a lot of your thicker soils will actually, when you're in mountainous areas, will be along stream. So that's something you might keep your eye out for where you are. If there are any small streams that don't have a lot of water, but where they've cut down through, sometimes that's a natural way to see deeper profiles.
Ben, I actually have a quick question.
Oh, Sam, yeah.
So, I wasn't able to dig, but I did go out and I kind of just picked up the soil to see how, and tried to do a few of the tests on it, but to see if I could distinguish anything special about it. But with my case, and I saw it also in the video, when he was forming that ball and spraying it with water, I mean, it seemed like he was losing a lot of possibly sand. Like it was kind of just falling out of his fingers as he was moving it around. And I wasn't sure how much of an effect that is, and if you wanted to have a more precise and accurate measurement, if there was another method you would have to do in order to catch that sand that fell. Because I just feel like that would kind of, I mean, he was saying oh, if it was super sandy, then it wouldn't have formed the ball. And I was like, yeah, it could have been super sandy, but you lost all the sand. You just dropped most of it. So
yeah, and
sorry, go on.
Yeah, sorry, didn't mean to interrupt, but just quickly, part of that was he was starting with relatively dry soil. So when he was crushing it in his hand, he was definitely losing some material, but maybe it's hard to say how much that biases, that you lose sand and not silt when you first crush it up, because you're breaking up everything. He made 2 ribbons from each of the things, right, just to kind of check. And it's good practice to do that, but make repeat measurements when you can. That gives you a little bit more confidence that your measurements are representative. But certainly, again, where you have access, ideally you collect samples from each of the horizons and then either bring them into the lab or send them to a lab where you can do more detailed textural analysis. So you can take the samples. You totally disaggregate the samples in water, for example, and you put the samples in sieves where you have different size openings in the sieves, and you shake the sieves, and the sieves will catch certain sizes of particles. And that's kind of the more quantitative way that you determine soil texture. And or like at Dickinson, we also have a laser particle size analyzer where you can take bits of the soil, very small bits, and put them into a machine, and the machine disaggregates all the little particles, and then basically shines a laser through the slurry of particle and liquid. And depending on how much scattering there is of the laser light, it's calibrated to estimate percentages of silt and clay and sand. So there are definitely lots of different ways you can do more detailed estimates. But it's useful, like I said, in the field, it's useful to practice these tests and a lot. Get your hands a little dirty. Like you said, don't wear your best clothes out in the field to do this unless you're trying to have an excuse to get a new pair of good clothes, and then maybe it's a good thing to do. But the reason it's important to do these things in the field is if you're looking at a soil horizon, especially if it's relatively thick, and you're trying to decide where you need to sample, to actually make measurements of things that are different. You might, if you have a thick B horizon, or, if you have a thick B horizon that's mostly the same color, if you're going to try to determine if there's a B1 and a B2, part of that determination might be based on texture. So if you've got 30, 40 centimeters of uniform thickness material, you might take a sample at the top and a sample at the bottom and do these tests quickly and just make sure that the texture isn't obviously different. And the more you do this, I think the more you'd get to it pretty quickly. Even just the feel of the sample without going through all the tests would be enough to tell you, yeah, these two things feel the same, or these feel a bit different, so I better do a more quantitative test. Yeah. Okay. All right. So hopefully that helps you visualize some of the field tests you can do. We're close to being done with most of the things that you would do in the field with characterizing soils. I will probably try to find a video that goes through doing things like the hydraulic conductivity, which we've talked briefly about, but essentially that's simply taking some sort of a cylinder volume where the volume, putting a known amount of water in it, and literally just with a stopwatch timing how long it takes the water to soak into the ground. And usually the first time you do that, you're getting something about the field saturated or the field conductivity, because if you're in an area that hasn't had rain for a while and you pour water in it, the pore spaces may not have very much water, so you may be at the low end of field capacity. But ultimately, if you do this 1 or 2 times, you fill it up, you let the water drain down, then you fill it again. At some point, you've filled most of the pore spaces now, and then you're looking at the saturated conductivity, and that tells you how fast gravity can pull water through the pore spaces to go down without so much water sticking as a film around the individual pores. Okay. So Friday we'll talk a little bit about roots and pore spaces and how you characterize those. It's relatively straightforward with roots. A lot of it's describing how big root burrows are that you can see, how much, sort of get an estimate of how many roots per square centimeter there are, and then the same thing with pore space. And a lot of these measurements, your main tool is simply the ruler on the back of your field notebook, right? We're just measuring the sizes and dimensions of things. Okay, good. So if there are no more questions, so for lab today, like I said, we're gonna probably do one local soil, which you can pick locally, and then I'll pick probably 2 other areas to have you go and look at soils to make sure that as you're filling out your soil description forms. And I think we'll shoot for 3, although we'll get a little bit of a sense of how long it takes. But if you do 3, then you're starting to get the feel for what goes into the peat descriptions. And there is a lot of information in the description that you can look up beforehand. Things about the location and the landscape and stuff like that. But that's going to be the main goal of lab today. And then obviously we'll go through the one in your book, because I do have a worked example in your field book to kind of show you what you should have in each thing. And then the lab will be due next Wednesday. Good. Okay. All right. So I will see you guys in 2 hours.